All right, so today I'll be looking at this thing that I've written on the board, which is known as a specific heat capacity. And what is specific heat capacity actually talking about? It's the same continuation from where we, or what we were discussing last week. We're just adding on some new things. So remember, uh, when we talked about movement of thermal energy from one area to another, specifically from an area which is higher, having higher temperature, to an area which is having low temperature, what we're supposed to know is that as you are supplying heat to a certain substance, or as you are supplying thermal energy to a certain substance, that substance will be experiencing what? Will be experiencing change in temperature, or will be experiencing a rise in temperature, a rise in temperature. What's the other one? What will be happening to the source where so it's maybe the scenarios can differ here because it's either you're getting your heat from a constant source which is not decreasing, or sometimes maybe you've just mixed different, or you've just mixed 2 cups of water where you're having uh water with a higher temperature mixed to water with a lower temperature. You're going to notice that the temperature of the other substance is going to be raising, the one which had initially lower temperature, whilst that the one which had a higher temperature, there will be a decrease. So it always takes some amount of heat in order for you to raise the temperature of a substance. Like this one that I'm talking about, to say you want to raise the temperature of a substance. If you're supplying heat to a substance, there's always a fixed amount of heat that we require in order for us to raise the temperature of that substance. And we call that heat capacity, or we call that energy, the amount of heat, amount of thermal energy required to raise the temperature of a substance. We call it as heat capacity. But if we want to be specific, and that's how I'm going to define specific heat capacity, we already discussed what this guy is when we're talking about water. We said one of the unique properties of water is that it has a high specific heat capacity. And what does that mean? That means we're going to define this term, specific heat capacity, as the amount of thermal energy. This is just heat capacity that I've written on top here, but the amount of thermal energy, like this, that is required to raise. I'll be using arrows pointing up to represent raising. The amount of thermal energy that is required to raise the temperature of a substance, or of 1 kg, because I want to be specific here. That's why I'm saying specific heat capacity of 1 kg of a substance by 1 degree Celsius, or sometimes we can use 1 Kelvin. It's the same, but here we are very familiar with degree Celsius, so we're going to be using 1 degree Celsius. So it is very, very important concept because it's telling us the actual amount of thermal energy that you're going to require to raise temperature of a substance, or temperature of 1 kg of a substance by 1 degree Celsius. And since different materials have different properties, you're going to find that also the specific heat capacities of substances are going to differ. Some substances are going to have low specific heat capacity, whilst some substances are going to have what? Are going to have a high specific heat capacity. So if a substance has low specific heat capacity, what does that mean? That means it is easy to raise the temperature. It is easy to raise temperature of that substance. But at the same time, since it's easy to raise the temperature of that substance, you're going to notice that it also loses its temperature easily. Even when cooling down, it is going to cool down at a faster rate since it's having a low specific heat capacity. So if it's able to heat up in a very short time, that substance should also be able to cool down at a very fast rate, because at the rate at which it is going to be gaining its energy, or its thermal energy, will be the same rate at which that substance is going to be losing its thermal energy. So it will be easy to raise the temperature of that substance, but it is also easy to cool it down. It's also easy to cool that substance down. Whilst if you're having a substance that has high specific heat capacity, you're going to take a lot of energy, a lot of thermal energy to raise the temperature of that substance, and you're also going to require a lot of energy or you're going to require a huge amounts of energy to be lost in order for that substance to cool down, or the rate at which that substance is going to cool down also be very low. It will be difficult to cool it down because it is having a high specific heat capacity, which means the amount the amount of thermal energy that is required to just change 1 kg of this substance, to raise the temperature of 1 kg of this substance by 1 degree Celsius is a lot. Hence, it will be difficult to heat such substances, whilst at the same time, it is also going to be difficult to to cool down such substances. So specific heat capacity can be represented by the letter C, like this. Mostly they use a small letter C, represented by the letter C, and it has SI units of joules, of which this is the specific or the SI unit for energy per kg degree Celsius, like this. Or sometimes you can just say it's joules per kg Kelvin. So these units are interchangeable, or you can swap between these two units of measurements. They are both considered the SI units for specific heat capacity, because the the units of measurements of Kelvin and degree Celsius are not different. They are the same. The temperature difference in Kelvin or their rate is the same. So you can either use degree Celsius or degree or Kelvin. It's one and the same thing. Or sometimes they'll just write it as joules, kg, degree Celsius, like this. Or even Kelvin, they'll just put joules, kg, Kelvin, like this. So it's one and the same thing. But what we're supposed to know is that these are the SI units for measuring the amount of energy that is required to raise the temperature of 1 kg of a substance by 1 degree Celsius. So how are we going to calculate the energy now that is required to raise 1 kg substance's temperature by 1 degree Celsius? We are going to come back to heat, because in order for a certain substance to increase in temperature, you are going to supply it with heat. And we said the letter that represents heat is the letter Q. Now, this Q, the amount of heat that you're going to supply to a substance, is going to be directly proportional to the mass of that substance, in kilograms. And also it's going to be directly proportional to what? To the specific heat capacity of that substance, which is represented by C, like this, and also directly proportional to the change in temperature. Change in temperature, of which this change in temperature is just representing what? It's representing final temperature minus initial temperature, like this. So this is the formula for finding the amount of heat that you're going to add in a substance. I'm going to say Q is equal to what? Q is equal to mass of that substance multiplied by specific heat capacity of that substance multiplied by what? Multiplied by change in temperature, which means we can rearrange this temperature if we want to find C, to say divide both sides by M over change in T, even this side divided by M over change in temperature, giving us the formula for calculating the specific heat capacity of a substance to be equal to what? To be equal to Q over M multiplied by change in T. And therefore, we can use this formula to calculate the specific heat capacity of a substance, which is basically the amount of heat that is required to raise 1 kg of a substance's temperature by 1 degree Celsius. Now, how can we measure heat capacities? Or how can we measure specific heat capacity? So there are two ways in which we can measure the specific heat capacity of a substance, or how we can find out the specific heat capacity of a substance. So this is the formula. Don't forget about this formula. Also, this one that I wrote here, these are very important formulas, such that I should never, or they should be on your fingertips. These are simple formulas that you should just know, where this formula that I've given you for Q is standing for heat or thermal energy. C is standing for specific heat capacity itself. M is for the mass of that substance, whilst delta T is the change in temperature. Now, I'm saying to say, how can we measure the specific heat capacity of a substance? So we can use two methods to measure the specific heat capacity of the substance. Two methods, of which one of them is by using electrical method. An electrical method. So the electrical method of finding out the heat capacity of a substance is usually, or is basically using an electrical appliance, which is going to be a supplier of heat to a certain substance, and we can use such to find the specific heat capacity of a substance. Because, for example, if you want to heat water, most of you, especially this cold season, you use elements, electrical coils to heat your water. So we can use those substances to measure the specific heat capacity of a substance. Why? It's because you know to say that substance, that electrical coil that you want to use is going to do what? It's going to supply power, certain power. It will be generating certain power that will be propagating heat into the substance that you want to change the temperature. So that power that is going to be supplied by that substance. We'll talk about these formulas more when discussing electricity. But what you know is that power that will be supplied by that substance will be equal to what? It will be equal to voltage multiplied by what? Multiplied by current. V multiplied by I. V is for voltage, whilst I is for current here. Now, by supplying power, this guy is going to be supplying energy, of which this energy is in form of what? Is in form of thermal energy. So I'm going to say energy is equal to what? Is equal to the power that we have, that this substance is rated, multiplied by time taken. So this will be equal to what? This will be equal to power multiplied by T, uh, um, like this. So if these are the two formulas, that the one is finding the power rating of a substance, one is finding the energy, which is power multiplied by time. Now, how much energy is going to be supplied by that heater or that electrical coil or whatever it is that you're using? So we're going to say energy, which is thermal energy, Q, will be equal to what? Will be equal to power multiplied by time, like this. This will be the formula that we're going to use to find the energy supplied by the heater. And we know to say the formula for power is this one, which is current multiplied by voltage, whilst we have time here. So which means we can simplify this formula to say Q is equal to what? Q is equal to V, which is voltage multiplied by current, like this, just representing power, multiplied by T, which is the time taken for that substance to heat up, like this. So the energy that is gained by water, let's now relate these formulas. If we're using this formula that I've written here to find the energy that is supplied by the heater, let's now calculate the energy that is gained by the water. So in order to say energy that is gained by the water, Q is equal to what? Q is equal to mass of that water multiplied by the specific heat capacity of that water, multiplied by what? Multiplied by the change in temperature of that water. So we're now going to equate these two equations. We're having this equation from the electrical appliance, whilst we're having this equation, which is relating the energy gained, the mass of that substance, the specific heat capacity of that substance, and the change in temperature. So I'm going to say V, this one. Let me just wrap some things so that they don't look a lot of dirt in here. Okay, so I'm going to equate this formula or this Q that is here to this Q that is here, because this is the energy that is supplied and this is the energy gained by the water. So I'm going to equate this guy to this guy so that we come up with one formula. So I'm going to say Q supplied will be equal to Q gained here. Like this. So that means I'm having VI multiplied by T, or VI T, which is the energy supplied. The thermal energy supplied should be equal to what? Should be equal to M multiplied by C multiplied by change in temperature, like this. So that means the overall formula for calculating the specific heat capacity will be equal to what? Will be equal to divide both sides by the mass of water multiplied by the change in temperature. Even this side, the mass of water multiplied by the change in temperature, like this. And I'm going to have one single formula which is going to tell me specific heat capacity of water will be equal to what? Will be equal to VIT over mass of water multiplied by the change in temperature. So this is a formula that we can use to calculate the specific heat capacity using the electrical method, of finding or measuring the specific heat capacity of a substance. So they like bringing such questions. They just tell you to say an electrical appliance, blah, 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 blah. And all you're supposed to do is apply this knowledge that is here. So this is the first method of finding the specific heat capacity of a substance, which we call the electrical method. Whilst the next method, we can just say it's a method of mixtures. This is the second method. We can just say this is what? This is a method of mixtures. So this method of mixtures, it uses the principle that is used under this method of mixtures is that when you mix two substances, the first example that I gave, say when you mix two substances where you have one substance that is cold and another substance that is hot. The substance that is hot is going to lose heat. The hot body is going to lose its heat to the cold substance, whilst at the same time, the cold substance is going to simultaneously gain heat from the hot substance until you reach an equilibrium temperature. Equilibrium temperature. So those who attended the last class, or if you didn't attend, I posted the video on my YouTube. I'm sure some of you managed to watch, and we already described what equilibrium temperature is. So there's simultaneously gaining and losing of heat energy by the cold body and the hot body simultaneously until you reach equilibrium temperature. So having this principle now, we are going to apply the law of conservation of energy. Conservation of energy, where we are going to assume to say there is no energy that is lost to the surrounding between those two substances. And if there is no energy, or if we put an assumption to say there is no energy that is lost to the surrounding, that means what we're supposed to have, we're going to say heat gained by the cold body. Heat gained by cold body should be equal to what? Should be equal to heat lost. Heat lost by the hot body. So this is the principle of conservation. So we're assuming to say there's no energy that is lost to the surrounding. Hence, we are saying heat gained by the cold body is equal to heat lost by the hot body. Now, using the equations that we found, the equations for the amount of heat that is applied to a substance when there's a change in temperature, we say the Q is equal to MC change in T, like this. So we're going to say Q gained should be equal to what? Should be equal to Q lost. As simple as that. But since this side, there will be a negative change in temperature. The substance is losing thermal energy. You're going to balance this side of our equation with a negative. So I'm going to put a negative sign in front there. So that means if let's say, for example, we're talking about water, I'm going to say the mass of water. I'm just plugging in this. The mass of water multiplied by the C of water. There will be change in temperature. So let's say, for example, we have, because here we're going to have three temperatures. There will be the initial temperature of the hot of the cold body, which we're going to call temperature 1 or temperature 3. Should I call it temperature 3? Okay, let's just call it temperature 1. Then there will be equilibrium temperature. which will be called the final temperature. Then there will be temperature of the hot body, which we are going to call the or T2, like that. So the change in temperature here is going to be what? It's going to be equal to the final temperature, which is T final, minus T1, like this. This will be equal to what? This will be equal to the energy that is going to be lost on this side. So we're going to say negative M, the mass of the water. Able to see what I'm doing on my screen. So I'm going to say M. I said there are three temperatures. The temperature of the cold substance, there's equilibrium temperature, and there's the temperature of the hot substance. So here on the cold side, I'm going to have my mass of the water multiplied by the C of the water multiplied by the change in temperature, which change of temperature we're having. It's T final minus T initial, which is T1. This will be equal to the energy that is lost. I'm going to say minus M minus M of water multiplied by C multiplied by the change in temperature, which is T final minus T2, like this. So this is how this formula is. Or if not, or if you don't want to involve this temperature or this negative that is here, that means you're supposed to interchange these guys that you have in the brackets. That means you're going to say M CW T final minus T1. This will be equal to M CW T2 minus T final. Since you know to say this one is losing heat on the other side, the final temperature is going to be lower than the initial temperature. Hence, you're going to have a negative sign here in the brackets. And to balance that negative sign, what are we doing? We're introducing this negative that is in front. So if you don't want to involve the negative, just make sure to say you swap them. You say the higher temperature minus the initial temperature, just like that, and it is still going to give you your desired answer, just like that. So that is the principle, or that is another way that we can find out the specific heat capacity, or the way you can measure the heat capacity of a substance. So the first one was a chemical method, or not chemical method, sorry, the electrical method. Whilst this one is the mixture method, where you're mixing different substances with different, or you're mixing substances with different temperatures, and you apply the law of conservation of energy. Okay, so just like that, that's the principle that we're supposed to know, or that's everything that we're supposed to know when it comes to heat capacities or specific heat capacities. So just know the formulas that you need to use. These formulas are not very complicated, such that you're able to memorize them. You're able to know them by your fingertips, and I expect you to do that. So that is all, ladies and gentlemen, on specific heat capacity. The only thing remaining is to look at some examples.